Yo, what's up, Mr. Who?
How's it going, George?
Pretty good, pretty good. How are you?
I'm doing not bad, not bad, not bad at all. Good morning, everyone. Hopefully, everyone is doing well. So as we're starting a unit today, this unit will be about the distances and stuff, a little bit more tangible than energy. So to start off, we have a warm-up problem. So my homegirl, Kylie Jenner, who I'm very good friends with, as you can tell. So she starts at home. I believe they live in Beverly Hills or is it Calabasas? Either way, they live in a very expensive area. And so she starts at home and then she walks 1.5 miles north to Starbucks. When she's at Starbucks, she gets her pumpkin spice latte, but she decides that Starbucks wasn't bougie enough for her. So then she walks another mile, 1 mile north to Phil's, because Phil's is the bougiest place of all time, and then she returns home. So the question we have today is how far did Kylie walk in total, and how far is Kylie from her starting point? Whenever you're ready, put your answers in the Zoom chat, and we'll see what people are thinking. Again, so Kylie Jenner, she's starting at home. She walks 1.5 miles north to Starbucks. She decides that Starbucks isn't bougie enough for her, so she walks another mile north to Phil's, and then she returns home. So how far did Kylie walk in total, and how far is Kylie Jenner from her starting point? So, Kylie Jenner, she starts at home. Good old Kylie, she walks 1.5 miles north to Starbucks. She gets a pumpkin spice latte because, well, she's Kylie Jenner. Then she decides Starbucks wasn't bougie enough for her. She walks another mile north to Phil's, and then she returns home. So we want to figure out how far did Kylie walk in total, and how far is Kylie from her starting point. We'll take another minute or two for people to figure this out. And we'll see what we can get. Take 1 or 2 more minutes. How far did Kylie walk in total? How far is Kylie from her starting point? So I'm going to just visualize it on the board here so that way everyone can see what's going on. So there's Kylie Jenner. She lives right here. So she lives right here. And so the first thing she does is she walks 1 mile north to Starbucks. Right. The next thing she does, she walks 1.5 miles north to Starbucks. Sorry. She walks 1.5 miles to Starbucks. And And then what she does, she goes another mile north to Phil's. Good old Phil's. All right, so what she's so far, she's gone 2.5 miles north. And then what she does is she goes all the way back from Phil's back home. And so if she goes 2.5 miles up, she goes 2.5 miles back down. So in total, she walks 1 mile plus 1.5 miles plus 2.5 miles. So in total, she walks 5 miles. So how far is she from her starting point? Well, I mean, she started at home and then she ended at home. So she's still at home. So there's a 0 change from her starting point. So she walked 5 miles in total, but there is 0 change from her starting point. So this will sort of introduce this idea of, position and distance. These are all kind of different concepts that we will sort of cover today. We will have some more celebrities involved today, but we're starting off with our girl, Kylie. Okay, so agenda today. So we're going to talk a little bit about distance and displacement. The slides and note sheets are all located on Canvas. So these are the link. I'm going to link the slides right here. And then the note sheet that you can fill out. So I'm going to give you a minute to open that up. And so you can take notes by hand. You don't have to use a note sheet. But if you want to have sort of something to help you take notes, I would recommend going through the note sheet. Yeah, and then when you are done, finish filling out your note sheet, just submit it on Canvas. And I should cover everything on the note sheet.
If we take notes by hand, do we just submit it in the same spot as we would submit the?
Yeah. Okay, so I'll give you a minute to do that. And then afterwards, if we have time, we'll move on to our first assignment of the unit, which involves reference points in Switchball. Yeah. So the first thing we're going to take a look at is our friend Waldo. So if you've ever done Where's Waldo before, what happens with Waldo is he's usually in Where's Waldo is like a comic, not really like a comic, but it's what's sort of like a problem solving thing. Basically what happens is Waldo is usually in like a massive crowd of people and you have to try to figure out where Waldo is. In this problem though, Where's Waldo is just by himself. But what I want you to do is in your groups, so I'm going to put you in your breakout rooms in a second. What I want you to do is in your groups, I want you to write down one sentence that describes exactly where Waldo is on the football field. So this is actually kind of tricky because we want to describe where exactly Waldo is on the football field. So this is something you want to think about, and we'll take a few minutes to see if we can work this out. But I'm going to put you in your breakout rooms, and I want you to try to write down one sentence that describes exactly where Waldo is on the football field. When I bring you all back, you can either just type in your sentence in the chat or you can share it verbally with the group. It's up to you. But I do want to try to have every group have one sentence that says where exactly Waldo is. So, and I'm going to open my room right now. Okay, rooms are open. All right. So either in the Zoom chat or you can say out verbally, I want you to share what your group came up with in determining where Waldo is on the football field. So you can type it out and say it verbally. Either is okay. But I want you to every group to share what they wrote down. Waldo's AFK. Good point. He is technically away from the keyboard. But where exactly is Waldo? Waldo is between the 10 and 20 yard lines on the right side of the field. Assuming that you are looking at it, the MA logo facing the right way. Ooh, that's interesting. That's interesting. Any other groups? Come on. Let's get a few more. I'll have to. Waldo's near the end zone on the 15-yard line, aka the red zone. Waldo's on the 15-yard line on the right side of the field, nearest the rest of the canvas. Okay, cool. Let's get a few more. There we go, George. Okay. We have a few groups who haven't shared with us yet. We'll wait. Okay, so we have a lot of good responses so far. What I want to sort of note down is how important it is to be as specific as possible. So, for example, if I were to say something like, okay, Waldo is, Waldo's is on the 20-yard line, for example, right? While it does give us a general idea of where Waldo is, there leaves a lot of room to interpretation. So if I were to say Waldo's on the 20-yard line, someone might say, hey, that means Waldo is right here on this 20-yard line. However, Waldo's on the other 20-yard line. So we need to make that more specific, right? And so this is where we have to, add some more specifics. If you say something like, the right side of the field, like that helps. That's definitely a very good step. But if you were looking at the picture rotated, right, the right side of the field would still be this side, right? So this can get really tricky really quickly. But I think in general, what I really like about all of our answers is we have a lot of key ideas. We need some sort of distance, right? We need to know how far away Waldo is from something. We need some sort of direction, right? Something like, the right side of the field is very good. And then last but not least, we need to have some sort of reference point, right? Something we're comparing Waldo's position to. So when we say the 10 or 20-yard line, right, we're comparing Waldo's position relative to, the end zone, right? So this is where we start talking about what we need in order to talk about position. So, dude, where's my car? So, great movie. Anyways, so if you ever parked in a parking garage, if your parents ever parked in a parking garage, if you've ever parked in a parking garage, so usually you need to remember where you park your car somehow, right? Especially if it's a big one. And so the position of your car is something we call the displacement. Right, the position of an object is the displacement. So when you want to remember the position of the car, you're trying to remember the displacement of the car. So when we want to figure out where we parked our car in a garage, we need to have some sort of reference point. So usually what you'll do if you is you'll look at the pillars around you and you'll find one that's labeled. So a lot of times you'll have one that says something like H3 or G2 or I5, right? You're comparing the position of the car relative to the pillar, right? That pillar is your reference point. It's something that you're using to sort of remember where your car is near. Then you need to know how far exactly, right, your car is from that pillar, right? So if I say, okay, my car is near H3, right? We still don't know, we have an idea of where it is, but we need to know exactly how far it is, right? The exact position. So then you might say something like, okay, I need a distance that our car is parked 10 cars over from H3, right? So okay, now we now have an idea. Okay, we know where to look. We need to look for H3. We know to look for something that is roughly 10 cars away. But still, right, remember that there's a lot of directions that we can look. We can look 10 cars up, we can look 10 cars down, we can look 10 cars to the left, right? The last thing we need is we need a direction, right? We need to know exactly where to look from this reference point, from this pillar. So this is where we say something like to the right. So then if I remember, okay, I parked my car 10 cars to the right of H3, what I can do is I can go to the H3 pillar, I can go 10 cars to the right, and I can find my car exactly. And the beauty of this is that if you tell any person in the world exactly, okay, where the reference point is, the distances and the direction, they can find where your car is unambiguously, without confusion, right? If I just said something like, I parked 10 cars over, right? That's not helpful because 10 cars over to what? 10 cars over from G2, from I5, right? You need something, you need a reference point to center it. And you just give us a reference point that doesn't tell us where the car is. It just tells us, sort of where to start off looking. So you need all three in order to be able to tell, to determine the position of a car or an object unambiguously without confusion. So let's say you decide, okay, I don't like this parking spot. It's a little too far from the entrance. We're going to get a lot of stuff from the store. So if we decide to repark the car, right, you're changing the position of the car. So in other words, when you are changing the position of the car, you are changing the displacement of the object, changing the displacement of the car, right? So position is displacement, they're the same thing, right? And so when you're changing the position of a car, you're also changing the displacement. Very important concept, these three things. So to continue sort of this talking about this idea of a reference point. So when you measure displacement or when you measure position, right, you measure it relative to a reference point. So, right, so if you ever had, you might have, honestly, you probably had a conversation, something like this, maybe not involving chocolate milk, but maybe something like my mom always asks me like where her phone is because she never knows where her phone is. And, right, so if I'm helping her out, right, I'm going to have some sort of conversation with her. So you might go something like this, like, yo, have you seen my chocolate milk? And someone will be like, it's over there, right? So it's over where? Like over here, or is it over here? It's just over there, like it's right here. Now you could have just told me that it was just on the table. So that's a conversation I guarantee you probably had at some point in your life. And the first thing I want you to notice is just how useless that conversation was. When you say it's over there, that is probably one of the least helpful phrases on the face of the planet. Over there what? Like over there here, over there where? Like it's completely useless, right? We need a reference point to determine the position of the object. Otherwise, we have nothing to base the position of an object off of, right? So that's why it's very helpful when you say something like, okay, like you left your phone on your desk, next to your textbook, on your bed, right? So like a reference point is one of the most important things that are helpful for determining the position of an object. So we need a reference point. And you can use different reference points for different things, right? We very rarely use the same reference point for positions of different objects. But usually we have some sort of reference point. So the next thing we need, we need a distance, right? So if we want to know the position of an object, we need to know how far away it is relative to the reference point. And this is what we call a distance, right? Distance is just how far away an object is relative to the reference point. So so if you go something like, okay, yo, I'm hungry AF, let's go get some Chick-fil-A. And then someone might say, hey, how far away is it? I'm not trying to drive too far. And then I might say, Google Maps says it's just 1.2 miles from here. So something like that tells you how far away Chick-fil-A is relative to the reference point. In this particular example, right, we're using the reference point, like our physical location. We're going to use the reference point here, and we're comparing the location of Chick-fil-A to our reference point, which is wherever you are here, and it's 1.2 miles from here. We'll I'll talk about this in the next part in a second, but it's very easy to get distance and displacement mixed up. They're two different things, and we'll talk more about the differences between the two. But I think I do want to iterate though is that it's sort of this. One of the things that gets kind of tricky is the position of an object can change depending on your reference point. So it can be 1.2 miles from where your home. It could be 20 miles from Costco. It could be 300 miles from New York, right, or LA. So you need a reference point to compare it to, and that's and then you also need a distance. How far it is. So we covered two things so far. We covered a reference point, the position, the sort of thing we're centering our position based off of, and then we need to figure out how far away it is. The next thing we need to know is we also need to know sort of the direction of the object relative to the reference point. So back to the Chick-fil-A example, if I say, hey, Chick-fil-A is 1.2 miles from here, we run into a couple of issues here. Is it 1.2 miles north? Is it 1.2 miles south? Is it to the right? Is it to the left? We still have no idea where Chick-fil-A is. We just know that it's 1.2 miles from here, right? And we can go anywhere in a circle and we can still never find it. If we add a direction, if we say, hey, Chick-fil-A is 1.2 miles north from here, now we know exactly where it is. And that's very helpful for telling the position of an object, the displacement of an object. So to summarize, you need a reference point, right? That's something you're basing the position off of. You need a distance, how far an object is away from the reference point, and then you need a direction. The direction is just, which direction is the object away from the reference point. Does anyone have any questions so far before we move on to sort of visualizing displacements? Okay, so the next thing we're going to take a look at is how you can visualize displacements. So usually when we look at displacements, we can visualize them sort of in terms of graphs and number lines, right? So when we visualize displacements, we usually need to set some sort of positive and some sort of negative direction, right? And usually on a number line or a graph, usually you set, the right side as being positive x, the left side as being negative x. On a graph, an XY graph, below the origin is negative y, above the origin is positive y, right? So in order to measure direction on that number line or graph, we need to set a positive and a negative direction. So in this number line here, we're using 0 as a reference point. In this XY graph, we're using 0 at the origin as the reference point, right? And objects in the positive direction have a positive displacement relative to the reference point. This got flipped. This one should be the other way around. I don't know why it says, it should be the other way around. It should be 1, 2, 3, 4, and then -1, -2, -3, -4. So sorry about that. But in general, objects in the positive direction have a positive displacement relative to the reference point, and then objects in a negative direction have a negative displacement relative to the reference point. So we usually will use something like, positive x, positive and negative x, or positive y, negative y. Those are the most helpful things for us in terms of measuring position. So I want you to, so we're going to take a couple minutes to try to check our understanding here. So in the Zoom chat, right, I want you to answer these questions. So first off, right, in an XY graph, what do we use as the reference point? So I want you to write that in the chat. What do you think is the reference point for an XY graph? And then I want you to try to answer, which side of the XY graph has a positive X displacement, which side of the graph has a negative X displacement. And the third one, I want you to take a look and see if you can identify, and this third one's a little trickier, we'll work through it. I want you to try to identify where the object's initial displacement is and which is the object's final displacement for each of the following diagrams. So we'll take a few minutes to work through this and see if we can work this out. And when you're ready, just put your answers in the Zoom chat. So for 3, see if you can identify the numerical displacements for each particular problem. Numerically it can be a little challenging, but let's see if we can do it.
Mr. Who?
Yes, go ahead.
I'm a little bit confused on the number 3, the graphs for the second one. It says 1 for the like first arrow, but then it goes from -2 to 4. So wouldn't that be like 6?
So, ooh, this is good. Interesting, very interesting. Okay, so what you're looking at is figuring out, so where you're actually jumping ahead here, which is cool. That's actually the change in displacement. That's actually how much the position changed by. The displacement is just, the initial displacement is just where is it initially, and then the final displacement is where is it at the end. It's not necessarily, it's not quite how much did it change by. It's just where is it initially and where is it at the end.
Okay.
We'll take a look at how much it changes by in the next part of this. But for now, just look at where is it initially before it moves, and then where is it after it moves. This can get kind of tricky. I'll take a couple more minutes to try to look at this. Okay, so let's take a look at this so far. So let's look at the first graph. So basically in this first graph, right, there's sort of two motions. It has the first arrow and then has the second arrow. So we just want to figure out where it initially starts off with. So I just look at where it starts off with. It's initially starting off at 1. And then it moves 3 over to the right. And then it moves another 3 over to the right. So at the very end here, the final is just 7. We're not looking at how much it changes by right now. We're just looking at where it is initially and where it is at the end. So in this one here, same thing. Initially, it's at -2. So this one's kind of tricky because it goes to the right and then it goes back to the left. So we want to figure out where it is when after it goes to the left. And so after it goes to the left, it's at 2. Oh, it's initially at -2. Sorry, it's at -2, and then it's at the end. It's at +2. And then at the end here for this third one, it initially starts off at -4. it moves 4 over to the right, and then it moves 6 back. So its final is just -6. So we're just looking for this one. We're just looking at where it is initially and where it is at the end. We'll get to sort of the changes in a few minutes. But hopefully you were sort of able to work through that. Does anyone have any questions about how I did things, what I meant by initial and final displacement? By initial displacement, I just mean where is it in the beginning, and the final displacement is just where is it at the end.
So is there any difference between position and displacement, or is that
They mean the same thing. Mean the same thing. Okay, so just to review, all right, in an XY graph, we use the origin as a reference point. On an XY graph, the right side has a positive X displacement, and the left side has a negative X displacement. And then for object 1, initial was +1, final was +7. Object 2 is a -2, +2, and then object 3 was -4 and -6. So the next thing we're going to take a look at is the difference between distance and displacement. The difference between distance and displacement is that the difference between distance and displacement is that the total distance something has traveled. So when I'm looking at a particular journey, like let's say for example, when Kylie Jenner is going to Starbucks and Phil's and then back, the total distance is just how far something has traveled without regard to direction. And then the displacement, on the other hand, is just your position, which can be positive or negative. You always have a position, even if you're not moving, right? And then your distance, on the other hand, it can never be negative, right? It doesn't make sense to, walk -5 miles because that's just not physically possible. Okay, so let's take a look at our friend here, Freddy the Fly. So Freddy the Fly is 6 meters away from a melted chocolate chip cookie. And so when Freddy the Fly flies over to eat this chocolate chip cookie, right, he is flying 6 meters. So the distance he traveled is just 6 meters. And we don't care about the direction. It's just 6 meters. Now, distance is just how far something has traveled without regard to direction. So again, Freddy has gone 6 meters. Displacement, on the other hand, is not only the distance Freddy traveled, but also the direction. So the distance Freddy traveled was 6 meters. The displacement, however, was 6 meters in the positive X direction. So the displacement here, we added a direction to it. And so because it has a magnitude, which is the distance, and a direction, displacement is a vector, if you know what a vector is. But it is a vector as a magnitude and direction. And so when we say Freddy travels, we're saying that Freddy travels through a displacement of 6 meters in the positive X direction. And so there's a key difference here, right? The change in displacement was 6 meters, and the change in the distance was 6 meters. So right now we're taking a look at the change in the distance and the change in the displacement. So In this particular example, this first circle is moving 15 meters to the right. So what we're going to do is we're going to say that this change in the displacement is at 15 meters. When circle B moves to the left, the displacement is 20 meters to the left. So the displacement would actually be negative 20 meters. The difference is that the distance for them is both positive. The distance A traveled is 15 meters and the distance B traveled is 20 meters. But there's no negative because distance can't be negative. It just went 20 meters. Whereas the displacement was 20 meters to the left. To sort of give you an example of what displacement versus distance sort of looks like. An example, if you're going from school back to your home, for example, the route you might take look like this, right? You're going this way, and you go up, and you go right, and you go up, and you go left. So the total distance you traveled is the distance of, you find the distance of each segment, and then you add them all together to know your distance traveled. The displacement is just a change in position. So you can think of it as the displacement as the bird flies. It's like a straight line. So displacement is just literally just what's the difference in position between the school and the and your home. Okay, so got another problem here. A girl T Swizzle. So T Swizzle in this particular story here, she starts her home in Nashville because she's from Nashville. So the beginning of her love story, she flies to Montana and she starts dating John Mayer. Of course, because it's T Swift, she breaks up with John Mayer because she knew he was trouble. And then so she flies to Scotland and then she starts dating Calvin Harris. She breaks up with Calvin Harris due to her reputation, and then she decides to move back home to Nashville to be with the one who had been here all along. So the question I have here is, what is Taylor Swift's displacement? And see if you can, and if you're ready, just put your answer in the Zoom chat. So Taylor Swift, she starts in Nashville, she goes to Montana, she goes to Scotland, comes back to Nashville. What is her displacement? If you have an answer, you can just put it in the Zoom chat. So this problem is kind of interesting because it honestly doesn't really matter where she went because she just started in Nashville and she ended in Nashville. So her displacement is just zero. She, in a sense, she didn't really go anywhere. She did have a lot of distance traveled because she flew across all these places, but her displacement is zero because she didn't move anywhere. She starts and ends in the same location. So that's actually something you should think about, is that if you start and end in the same place, right, your displacement is just zero. So for our last sort of check your understanding problems, I want you to think of an example where the distance and the change in position, or the distance and displacement, are the same. And and think about an example when they are different. And then for the diagram, I want you to determine the object's overall change in position from the beginning to end, and the object's total distance traveled. So last time we just looked at the initial and final positions. This time we're looking at how much the position changed by. And this can get kind of tricky because how much the position changed by is different than how much distance traveled. So we'll take a few minutes to see if we can figure out how much the position changed and how much the distance traveled changed. Whenever you're ready, put your answers in the Zoom chat. Figuring out the displacement should be actually not too bad because you know the initial and final positions. And so that should be fairly straightforward to figure out. The total distance requires a little bit of adding up the various arrows, but I think it shouldn't be too bad either. So see if you can figure out the displacements and the distances traveled. Take a couple more minutes and then I'll work through our number lines here. All right, so I'm going to start working through these number line ones. So what is one example where distance and change in you're just changing position, which is displacement? What is one example where distance and displacement are the same? So one example when they're the same is something like when Bryn was saying, there's only one, like when there's only essentially only one arrow, when you're not like switching directions and stuff, right? Then your distance and change of position are going to be the same. One time when they are different is if there's multiple arrows essentially, like in different directions, or if you're moving in the negative direction, in which case your distance would be positive, but your change of position would be negative. Your displacement would be negative. So those are some examples of when they could be the same or they're different. I'm going to quickly just start working through some of these number lines here. So to figure out our displacement, it's actually pretty, because we already did pretty much all the legwork that we need to do for figuring out our displacement. So the displacement is literally just the difference between the initial and the final position, right? Basically how much did our position change? So if we in the first number line, we initially started off at 1 and we ended at 7, which means that our displacement was positive 6. Right, our position changed by positive 6, and our distance is also 6, right? Then this is one example when they are the same, right? We're moving basically only one direction the whole time, and we're moving in the positive direction. So in which case, our displacement is the same as our distance. This is probably the most straightforward one. The next one here is going to be a lot more challenging. So this one, we have a multi-directional problem where we go we first go right, and then we go left. So we initially start off with an initial position of -2. We ended with a position of 2. So our total our displacement, right, how much our position changed is just 4. Right? Our position changed by positive 4 because we went from -2 to positive 4. However, our total distance is not 4. And this is because we actually went 6 to the right and then we went back. So our total distance here is actually 8. And this is one example when they are different, right? We went 6 to the right and then we came back 2. So our total distance is 8, but our position is only 4, positive 4. Our position only changed by positive 4. This one here is probably the toughest one out of all of them. But let's take a look at our displacement. So our displacement here, we started off at -4, and then we moved, and then we ended up at -6, our position. So our displacement is just -2, right? Our position changed by -2. However, our distance, we went 4 to the right because we started from -4, and then we went to 0. So we went positive 4. Oh, we traveled 4, and then we moved 6 back. So we traveled a total of 10. Right, we went 4 and then we went 6. Notice how these are always positive no matter what happens, right? And that's because your distance is just how far you went. You don't actually take into account your direction. So as long as you keep going, even if you keep switching directions, right, your distance is always increasing. It can never be negative. Your displacement, on the other hand, is just how much did you go to the right or how much did you go to the left. So if you go to the right, your displacement is going to be positive. If you go to the left, your displacement is going to be negative. And so, and our displacement here is just basically our change in position. So the difference between the two will be quite important. So it's very important to sort of recognize the difference between the two when we start moving on to other concepts involving distance and displacement. So I'll just take a minute to just sort of get these concepts solidified. So you can really grasp the difference between displacement and total distance. Yeah. So before I wrap up, does anyone have any last minute questions about distance and displacement position? Okay, so we will start our first assignment of the unit on Thursday. So again, no homework or anything. And because Wednesday is a Veterans Day, no asynchronous assignment either. So I guess, I mean, if you haven't finished any of your power or work assignments, I would, just continue working on those. Otherwise, you are free to go. You can, see you on Thursday. If you have any questions right now, or if you need any blanks that you want me to help you figure out, you can stay up. You can stay for the next couple of minutes. I'll try to answer them for you. Miguel, which blanks are you having trouble with?
Thank you.
Thank you.
Thank you.
Thank you.
Bye. Have a good day.
Okay. So, okay, let's see.
Hey, Mr. Who?
Yeah.
I need from 4 down. I couldn't find those in the slides.
Okay. Yeah. Hold on. Okay. So, okay, let's do this. Okay. So, in order to establish the position of an object, we need to have a reference point. We need to have a distance, and then we need to have a direction. I changed up the wording of this slightly recently. When an object's position changes, we can see that the object had a displacement. Position is measured relative to a reference point. Let me know if I'm going too fast.
Mr. Hugh,
Yes, go ahead.
so you said in order to establish the position of an object, we need to have a reference point. And what were the other two?
A distance and a direction.
Thank you.
So when we need to figure out how far away an object is, this is what we call the distance. We also need to know the direction of the object relative to the reference point. This one here is just, we often use number lines and graphs, XY graphs, to show the position and displacement of an object. So number lines and XY graphs. So to measure direction on a number line or graph, we need to set a positive direction and a negative direction. So we need to set a positive direction and a negative direction. So because of this object in the positive direction, right, they'll have a positive displacement relative to the reference point. And then objects in the negative direction will have a negative displacement relative to the reference point. These are the check your understandings. They should be on the slides. So I'm not going to go over these, but I will go over these though.
Mr. Who?
Yes, go ahead.
I need the fourth bullet point. Displacement is measured blank to a blank.
Displacement is measured relative to a reference point. Relative to a reference point. Okay, and then I'll go over these last ones here. So total distance is how far something has traveled without regard to direction. Distance and displacement are not the same thing. And this is because your displacement is your change in position. And so this can be positive or negative. and you always have a position, even if you're not moving. And distance, on the other hand, can never be negative. That should be all of it. Miguel, are there any other ones that you missed?
All right, thank you.
This is blank.
Sorry? Miguel, what was the other one you missed?
Total distance is blank. Something has traveled without regard to blank.
Oh yeah, total distance is how far something has traveled without regard to direction. Without regard to direction. Anything else? George, anything else?
No, I'm fine.
Okay, cool. Maria, do you have any questions for me, Lucy?
Mr. Hugh,
Yes, go ahead.
3 and 5 again, like from the top.
Yeah, okay, 3 and 5, okay. Is this displacement is measured relative to a reference point? Is it that one?
Sorry, what?
So if I displacement is measured relative to a reference point, is that the one you're missing?
It's the one that says position is measured.
Oh, yeah, sorry. It says position is measured relative to a reference point. Relative to a reference point. And then 5 is we need to know the direction of the object relative to the reference point.
Mr. Hugh?
Yes.
Which one is the one that says when an object's position changes, we can say that the object had a blank?
Displacement. Had a displacement.
Okay, thank you.
Mm-hmm.
Arma 2. I got everything. Thank you.
Got everything?
Yeah.
Okay, cool.
Peace.
Okay, see you, Miguel. Maria, did you get everything? Did you have any other questions for me?
Yeah, actually, sorry. The one that says to measure direction on a number line or graph, we need to set a blank direction and a blank direction.
We need to set a positive direction and a negative direction.
Okay, I think I finished, yeah.
Okay, cool, perfect.
Okay, thank you so much, Mr. Hugh.
Bye-bye.
Bye.